Thanks, Hannes. So my name's Henry. I'm a third year statistics PhD at Stanford, where I'm jointly advised by Brian Tripp as well as Scott Linderman, who are both affiliated with the statistics department.
Yeah, and I'm Nate. I'm a second year CS student and co-advised by Brian Tripp and Anshul Kindaje, who's in the genetics and CS departments.
Yeah, great. And today, Nate and I are going to chat about our recent paper, Calibrating Generative Models to Distributional Constraints, which we're super excited about and really deals with the issue of fine-tuning generative models, including autoregressive language models, diffusion models outside this traditional reward fine-tuning setting. So excited to present our work. And yeah, thanks for joining and listening.
Cool. So yeah, we're going to talk about calibrating generative models. So what do we mean by a generative model being miscalibrated? So for this talk, we'll say a model is miscalibrated if the expected value of some features, which we'll find from data with this function h of x, doesn't match a target value h star. And one example might be if we have an indicator function. Let's say we have an image generative model, and our h function is an indicator of whether there's a cat inside the image. Then we say our model p theta is miscalibrated if the probability under the model that a cat is in the image doesn't match some target proportion h star. And why might this happen? One common reason might be bias in the training data. So that could be there's just the wrong proportion of cats in our training image data set. Um, Another possibility is just that training neural networks, there's like no guarantees about finding. Oh yeah, go ahead.
Yep. Also, feel free to always keep going until you think it's a very nice time to take a question. So here now you're already saying there's an H star instead of saying something like we have some other distribution and then the expected value with respect to this other distribution is what we talk about. And is that, yeah, do you have like particular reason for making it H star instead of the expected value of some other distribution?
Yeah, I guess H star is like a bit more flexible potentially because we can also like the last bullet point in this is like H star is a design constraint. It doesn't have to come
Mhm.
from real data in any way. Yeah, so like that example, maybe we just kind of want an unnatural proportion of cat images. It's not coming from any specific distribution.
Yeah.
Yeah, and then so like I was just talking about suboptimal like training. Maybe just quickly mention because this comes up later in the talk, these post-training adjustments reason for having a miscalibrated generative model. So like low temperature sampling is very common in autoregressive models and masked generative models. And then low noise sampling from diffusion models is also very common. And those are both basically heuristics and change the output distribution from uh, the distribution the model was fit to. So that yeah can introduce miscalibration. So one example we'll talk about is diversity of protein structure diffusion models. So yeah, this group doesn't need to hear that protein structure diffusion models are very important design tools. There's this motif scaffolding problem where you have some functional motif and you want to build a protein structure around it. Um, and then there's also this protein binder design problem where you have a target and you want to design a structure to bind to it. And both of these have been very effectively done with protein diffusion models. Um, but there is a problem, which is that in order to get very high quality structures out of these models, typically post-training heuristics are used at sampling time. Um, but these heuristics come at the expense of reduced structural diversity. They basically trade designability for for decreased diversity. Um, and yeah, we see that in these plots here. So the left plot shows the distribution of alpha helix and beta strand proportions from this cath database, which I think represents a decent distributional target for having a diverse set of protein structures. The middle shows what happens when we sample from Genie2, which is one of these recent structure diffusion models. And if you sample at the noise level for the diffusion model that basically the model was trained for, you see a pretty good diversity of secondary structure proportions. But you only get 26% designability, which is a pretty reasonable quality metric people use. And then on the right, if you use a trick from the paper, which is to just set the noise level at sample time for the diffusion model to half, um, then you get 98% designability. But you can see that we pretty much always get the exact same proportion of alpha helix and beta strand in those sampled structures. And so basically, we either see that we can get very good designability, but very low diversity, or we can get good diversity but bad designability. And so the question is, can we get the both? Can we get both at the same time?
Mm. Yeah, what
Yeah.
if the reason why we're getting low diversity is just because the um, like what if the reason, or let's imagine that Genie sampled at temperature 1 just generates and designs perfect proteins actually, and it reproduces the data distribution where we have our strong binders in there. But now
Yeah.
we have this designability metric, which like the natural proteins aren't even designable. Or these types of proteins that bind strongly, they are just not even designable. And now, yeah, only because of that reason, the middle plot has the 26% designability.
Well, we calculate the designability for cath, and it's much higher than 26%. Um,
Okay. What do you get?
so
Do you
it's
remember?
Something around like 60% or something like this. You're right. It's not as high as like 98%. A lot of these like natural cath domains are also like not designable, for the reason that you said, Hannes.
Yeah.
we'd like to
Then
get it
we
higher at least.
could imagine the designs now being a little bit out of the sequences that the model has seen during training a bit more if we now generate with the diffusion model because they're kind of novel sequences. Then the folding model struggles a little bit in folding them up as well. And then we expect to not see 60%, but like 30. And then we would have the number. But all this is just wild speculation, right? I don't know. So let's continue with this premise because definitely that's what we're doing right now, right? And we do need the designability check for most of our design tools and see that to be valuable in practice, just empirically, if we look at the end at wet lab result numbers.
Totally. I think,
Yeah,
yeah, your point is, I guess, yeah, this designability metric doesn't perfectly correlate with like this biophysical plausibility that sort of we hope it's sort of a proxy for, and that's totally a valid point. It's not a perfect metric by any means.
But so even if like it were totally the case that it's
Mhm.
completely flawed or so, right, this wouldn't even matter here for the type of question that we're asking because let's say we're just doing an exercise here of because certainly there are applications where this type of calibration is perfectly applicable. And yeah, I also do think that is applicable here, and it would be useful to incorporate in some models, including Bayesian, for example. Okay, sorry for the long tangent.
No, good point.
no, no worries. Yeah, it's a good question. Yeah, so another example we'll talk about in the talk um, is this gender occupation bias seen in large language models. So the basic problem is that LLMs inherit gender bias from their training data. So we have this example when sampling children's short stories from this recent-ish LLM called Gemma 2, that when it generates short stories with a lawyer character, it only uses a female name for the lawyer 3% of the time. Whereas as of 2024, 41% of attorneys in the United States are female. So it's not even that it's like reflecting society's bias. It's even worse than society's bias. Um, and so this plot here shows on the y-axis gender imbalance and then broken down across 14 different professions. And so you can see that across all the professions, there's pretty high gender imbalance when using kind of a just a prompt asking for short stories. That's those hatched bars. And then if we use a prompt asking for balanced genders in the short stories, then for some of the professions, like judge, it helps a lot, but it definitely doesn't solve the imbalance for all the professions and only decreases it slightly for most of them. And so we can't just easily solve this problem by prompting. And so this is where our CGM, our method, will come in. And yeah, with that, I'll hand it off to Henry.
Yeah, great. So Nate motivated two particular examples in generative modeling where our distribution from which we're sampling might have some properties or some statistics that deviate from these sort of like target properties. So this really leads us to our framework. We're first going to like formulate what I mean by this generative model miscalibration problem, which we briefly outlined at the very beginning. Then we're going to discuss the relationship of this calibration problem to a related problem of reward fine-tuning, and in particular, why existing reward fine-tuning algorithms really won't solve this problem. And then we're going to present this calibrating generative models or CGM framework, wherein we propose two particular algorithms to solve this problem. And we're going to finish off by returning to the two particular case studies that Nate presented and show that by applying our algorithms, we're able to reduce a majority of the miscalibration in these two particular settings.
Can I add on to your examples? Because you just had this list of examples where you have these calibration,
Hmm.
where calibration is helpful. And
Hmm.
now I'm thinking the like a example that we've seen in the past, people trying, and something
Hmm.
where it seems, or this seems super helpful to me is
Hmm.
if you have like you want to train your generative model for a certain distribution, and now you
Yep,
have some data that comes from the distribution, but you also have data about observables about the distribution. And now
exactly.
you just want to use both types of data for training. So like
Yep,
the case of your web like bioemu, where
exactly.
we want to generate the distribution of structures that a
Yep,
protein takes on. And now we then have some folding energies or some free energies of stability of the protein. And then we can fine tune on these observables to make sure that, and there we definitely have exactly this problem.
exactly, Hannes. Yeah, we're actually thinking about this exact problem now where we're working in this bioemu
Yes.
setting where we're interested not in just generating like single structures, but from these conformational ensembles. And like you said, we don't actually have like some given reward as we do in reward fine-tuning to tell us like which sample should we upweight or downweight from the base model, but we have these like ensemble level properties like these like folding stability measurements or these folding proportions from this like Tsuboyama mega scale data set. So yeah, there's many examples in these protein ensembling model cases where we'd have these like distributional properties of like the known conformational landscape of these structures that we'd want to incorporate into our pre-trained model in
Yeah.
some way.
Nice. Yeah, we had BioEmu on here also a while ago,
Mhm.
maybe a year ago or
Mhm.
something like this. And then also most of the presentation, like we discussed the this fine tuning that they do to
Yeah.
adhere to these observables. And I suppose now we maybe have a potentially more principled path here. So let's see what
Mhm.
that is.
Great. Yeah. So to formulate our problem, we'll work in this traditional like fine-tuning setup for generative models wherein we have some pre-trained generative model, which we call P theta base. And then, like Nate said, we'll have this calibration function h of x, which is our sort of observable of interest. And then we'll have this calibration target, which we'll call h star, where h star will be just a vector or a scalar, depends on the dimensionality of the constraint. So if our base generative model is miscalibrated, we'll want to find another generative model P theta that is calibrated, meaning that this model should satisfy that the expectation of our observable under the generative model is equal to H star. So one issue that might jump out here is that there might exist many generative models satisfying the constraint. For instance, in the cat example that Nate provided, we could have um, where we want, say, 60% of our images to contain cats, well, all of those cats could either be black cats or all of those cats could be tabby cats. So there's not just like a single generative model in general which satisfies this expectation constraint. So we have to ask ourselves, among the many generative models that satisfy this constraint, which one do we in particular want to select? So what we do is we select the model which is closest in KL distance to the pre-trained generative model. So what we have here is we want to find the generative model P theta that is closest in KL distance to the pre-trained generative model P theta base, but now also satisfies this calibration constraint. The expectation of h of x under this fine-tuned model is now equal to h star. So just as a sanity check, if our base generative model already satisfies this constraint, then the optimal P theta will just be equal to the base generative model. So like I said, the idea is to find the closest generative model to the base generative model that satisfies this constraint. And pictorially, what this looks like is this. We have this class of generative models, which we denote as this big purple blob. And then we have this set of distributions which satisfy this calibration constraint, which we have with this black dashed line. And what we want to do is we want to find the model belonging to this purple blob that is closest in distance to the base generative model, but lies along the black dashed line, meaning it does satisfy the calibration constraint right here. So I think it's a reasonable idea to choose this particular solution because we don't want to deviate arbitrarily from our pre-trained model. Hopefully, our pre-trained generative model will encode some useful information about the training data. For instance, in these protein diffusion models, our base generative model tells us something about the 3D structure of this protein. So we don't just want to allow our generative model to move arbitrarily far from this pre-trained generative model. We might produce proteins in this case that look very highly implausible or unreasonable. So that's sort of why among these many solutions to this calibration problem, we want the one that remains closest to this pre-trained model. Okay, hopefully this problem formulation makes sense to everyone. So now we'll discuss the related problem of reward fine-tuning, and in particular, why existing reward fine-tuning frameworks won't allow us to solve this problem. So many people here are probably familiar with reward fine-tuning, but it's this popular framework within both language modeling, diffusion models, and generative models more broadly, wherein the user specifies some reward function R of x, and the goal is to find a generative model P theta that both remains close to the pre-trained model and maximizes the reward R of x. So your objective is saying I want to stay close to the base model, but I also want to make the reward under my fine-tuned model very large. And one can show that the solution to this problem is actually given by this closed form solution, which is just equal to the base generative model tilted by this exponentiated reward factor right here. This is well known. And yeah, this is sort of the classical reward fine-tuning framework. But note that this isn't the only way to sample from this tilted distribution right here. So reward fine-tuning will actually modify the weights of the pre-trained generative model, but there's also these inference time guidance strategies that don't require fine-tuning a model, but you can just sort of use these SMC or sequential Monte Carlo based approaches to sample directly from this tilted distribution without actually doing any fine-tuning. One of the, yeah, go ahead, Hannes.
And I guess then you can also combine them, right? Because for training with the reward fine tune or training with the first objective, trying to train a model for something
Yep.
that finds a solution to the first objective,
Yep.
then you kind of need to sample the base generative model.
Yep.
And now you can instead sample the base generative model already tilted with some inference time methods, and then
Yep.
use that stuff for fine-tuning your model. And now I'm
Totally.
thinking when we then afterward later have, but then you sort of need to debias the tilted samples that you
Exactly.
get for this
Yeah.
fine-tuning. And now I'm thinking when we later get to your framework, can we remember to maybe talk about whether that's also possible there?
Sure. Yeah, let's do that. But yeah, it's definitely possible to do, like you said, take combinations of these two. And yeah, both of them are sort of very common strategies taken. For instance, like Brian Tripp, our advisor, came out with Luhan Wu in 2023, this twisted diffusion sampler paper that uses this sort of like inference time guidance strategies for like this to solve this motif scaffolding problem. So reward fine-tuning is not the only framework out there. There's also these inference time guidance strategies, which are quite popular in this protein design space. And like Hannes said, there's not sort of just one way to do this, and you can sort of take combinations of them. But like you said, Hannes, you do have to account for the fact that you're sampling from a different distribution, sort of when you're actually optimizing the objective. So the point of bringing up reward fine-tuning is that it actually looks a lot like the objective that we introduced in this calibration problem. We want to stay close to the base generative model, and we want to satisfy a constraint. Although in this objective, you'll see that this is just an unconstrained objective. There's not a constraint here. So the difference between reward fine-tuning and generative model calibration is the fact that under our fine-tuned distribution that we get from reward fine-tuning, we want the reward to be large at every single sample that we draw from this distribution. So if I draw a sample from this reward fine-tuned distribution, I want the value of the reward at that sample to be high. Whereas in this distributional level calibration, it doesn't really matter to me whether the value of h of x is large or small at a given sample that I draw from the fine-tuned distribution. All I care about is that on average, it will be equal to h star. So the point is in this reward fine-tuning framework, I care about imposing individual sample information on my pre-trained generative model. Whereas in this calibration problem, I don't actually care about the value of h of x at any given sample that I draw. What I care is about this like ensemble level information, that the expectation of h of x under my fine-tuned model will be equal to h star. So they're sort of like solving two different tasks. Like I said, reward fine-tuning wants large reward for every single sample. Generative model calibration just cares about the expectation of this statistic under our fine-tuned model. So they're solving different problems, and moreover, a priori, there's no notion of a reward in this calibration problem here. And lastly, I also wanted to flag the relationship between this calibration problem and conditional generation. So if we choose this constraint function to be h of x being the indicator of a set A, so I want the proportion of samples that I draw from this set A to be equal to h star, and then I send h star to 1, then the calibration constraint becomes exactly that under my fine-tuned model, I'm always sampling from this set A. And what you can do is you can work out some math and show that in this case, the solution of the calibration problem that we wrote down is exactly equivalent to just sampling conditionally from the base generative model. So in this case, you can view this calibration problem as almost a generalization of conditional sampling from a generative model, wherein we choose our calibration constraint to just be the indicator of that event, and then we choose our h star to be equal to 1. So by like applying our calibration framework in this setting, you can actually do conditional generation, as I said, like you would do via an SMC-based approach, for instance. So hopefully this will sort of frame this calibration problem within related work. Like I said, the main takeaways here is that this can't be solved with reward fine-tuning algorithms, which really care about modifying the pre-trained model at the individual sample level, whereas we care about this ensemble level information. And moreover, by choosing a particular incarnation of our calibration function h of x, we can really recover conditional generation as a special case of generative model calibration. So now we'll get to our particular framework, this Calibrating Generative Models, or CGM framework, which will take a approach to solving this generative model calibration problem. So like I said, here's the objective that we want to solve: find the closest distribution in KL to the pre-trained generative model subject to satisfying this expectation constraint. And we'll propose two different algorithms, CGM relax and CGM reward. CGM relax is inspired by penalty methods from the optimization literature, wherein we relax the constraint by putting it into the objective itself. Whereas in CGM reward, we make a clever connection to this principle of maximum entropy to actually turn this problem into a specific reward fine-tuning problem for a very particular choice of the reward function. And our framework is very general insofar as all that we require of the generative model is that we can draw samples from it, we can compute log likelihoods, and then we can also compute gradients. So this is sort of encompasses a very large class of generative models such as normalizing flows, diffusion models, autoregressive language models, many of our tried and true favorite generative models out there. So like I said, it applies to a very broad class of generative models. And prior works that have tackled this same generative model calibration problem have only been applied to very particular model classes. And moreover, we show across all of the applications that we study in our paper, two of which, like I said, we presented at the very beginning, our framework reduces a majority of miscalibration. It's very computationally inexpensive. You'll know that these large language models are trained on hundreds or even thousands of GPUs for many days, and we're able to do all of our experiments in less than 2 GPU days on a single H100. So this fine-tuning step is very lightweight and also very effective. And moreover, our framework scales very nicely to very high dimensional constraints. So this h of x, like I said, could be a scalar, it could be a vector. So in this protein diffusion model example, we'll show that we're able to simultaneously calibrate our generative model to 99 distributional constraints at the same time very effectively. So now that I've sort of given this overview of our algorithm, Nate will present sort of the first algorithm CGM relax.
Yeah, so Henry presented this fairly difficult, potentially to optimize problem because it has a constraint, it's non-convex. So yeah, how do we start approaching optimizing it? And one approach is to relax the objective. We can turn the constraint into a penalty term, and we can turn the KL term into a sort of weighted regularizer. So intuitively, we put this. Oh yeah, go ahead.
That's sort of what I like, right? That's kind of like um the objective that we have in our, if we want to tilt with rewards as well. We just now define this new reward, which is the distance from the optimal, like from the observable. And that then, yeah, wouldn't you
I
say
think
this is kind
that's
of,
it's
yeah?
very similar, but and actually Henry will show like soon the connection between reward and uh, CGM, but uh, the difference there is that that would still be like if you just do it simply as distance from the average, the typical reward fine-tuning step would or reward fine-tuning methods would still be defined per sample. So you might end up with an objective that says move every single sample towards the mean rather than moving the mean of the distribution towards the target mean.
Yeah. Um, um, like I could also define my reward or my per sample reward to just ignore the sample and then um, be about the some property, some expectation or so of my distribution. No?
Mm.
Let's see.
Yeah, traditionally in reward fine-tuning, you'll specify your reward on the individual sample level, and then you'll say, I want to maximize that in expectation. So yeah, I think Nate's point was that if you,
Yeah.
yeah, sorry, I guess your point is you could sort of define something that's like maybe a very slight modification of reward.
Anyway, in the end, it's just semantics. Let's
No,
see
yeah,
what
yeah,
happens.
yeah, great, great.
Yeah. Yeah, so yeah, maybe real quick. So we turned the like KL term. We basically just put a lambda in front of the KL term, and uh, basically intuitively, if we set lambda to 0, then we have no regularization, and we'll start to approach the like true optimization problem that we posed before. And then if we set lambda very high, then we won't move very far away from the base model, and we'll won't fully satisfy a constraint. So lambda lets us trade off between how far we move from the base model and how closely we follow the constraint. Um, and so our goal will be to get unbiased gradients so that stochastic gradient descent type methods will work well. But even still, we need to allow for non-differentiable constraints H. So it's still not totally obvious, even with this penalty objective, how to get effective unbiased gradients. So we apply two tricks to get unbiased gradients. One is that we use the fact that the L2 penalty has a nice unbiased estimator. Um, and that's similar to like a bias variance decomposition. And a lot of other penalties you could think of, like an L1 penalty, there's no obvious distribution-free estimator for it. So it sort of justifies using this L2 penalty. Um, and the other trick is this important sampling identity that lets us move gradients inside the expectation. And so basically, we treat our samples as coming from a stopgrad version of the parameters of our model, and then we can move the gradient inside the expectation. This is also related to like score function trick and reinforce.
Okay, so if you go back one slide, then you're saying here the purple one in our objective at the bottom, that if we now just have our axes that come from our generative model, right? Then we can't backprop, or if we just backprop through the generation of those and then add this to our gradients as well, then we will end up with biased gradients. And now the usual thing of doing a stop gradient then is correct because of the second explanation and at the bottom of your next slide. But there's also something different that we can do to debias them. So this first thing on the slide. And now, is the first thing better in some way?
Yeah,
Oh,
so
we use both of them at the same time. Yeah.
Hmm.
Go ahead, Aaron. Yeah, you can.
no, yeah, so the point is like Nate's point is like if like we want an unbiased estimate, like we actually can't compute the expectation of h of x under our generative model in closed form, right? So what we're going to do is we're just going to draw samples, like you said, Hannes, from our generative model p theta, and then plug in like a Monte Carlo estimate for the average. But you can actually show that if I only look at this first term here in this equality, this is actually not an unbiased estimate to this like squared norm difference between the expectation and h star, and comes from like Jensen's
Ah,
inequality.
okay,
So what we
okay.
do is we compensate for the bias via this like added variance term, which essentially will like
Yeah.
debias and give us now unbiased estimates to this squared norm difference. Does that make sense?
Yep, yep, yep. What I said was wrong. So yeah,
No,
good,
no, yeah. No,
thanks.
that's a good point. Yeah, I don't think we explained that well enough. And then Nate's point is like once I have this unbiased gradient, sorry, once I have this unbiased estimate to the subjective, how do I actually like auto diff through
Yeah,
it? And then the way there is like, yeah, you set your weights to just like the stop graded version of your current weights.
yep.
Yeah, and it
Alrighty.
basically yeah, and we have like more detailed derivation in the paper. And yeah, it's not too hard to show that like with these two together, you get unbiased gradients, which it turns out in the experiments we have is enough for uh, in our case, Atom to work very well, uh, optimizing the CGM objective.
Yeah,
Cool.
Uh,
great. So Nate discussed this first approach, the CGM relax, which the idea, like Hannah said, is very intuitive, is just to turn this constrained optimization problem into an unconstrained problem by just shoving the constraint into the objective. What we're going to take in this CGM reward framework is a sort of different approach. We're going to show that this relates to a particular reward fine-tuning problem. In particular, first we have this calibration problem here in the top. Like I said, this is the one I've shown time and time again, which is just find the generative model that is closest in KL distance to the base generative model subject to satisfying these expectation constraint. But very related to this calibration problem is this well-studied problem in statistics, which we call the maximum entropy problem, which is to find the distribution P that is closest to the base generative model P theta base that satisfies this expectation constraint. And you might be looking at these two things and being like, oh, they look identical. Like, what's the difference here? The difference here is that in the maximum entropy problem, P doesn't need to belong to the class of generative models. So in the calibration problem, we're interested in finding a generative model P theta that is closest to the base generative model. Whereas in the maximum entropy problem, we allow P to be any distribution. It doesn't have to belong to the class of generative models. So the
this is actually something where I was typing out a question to put into the chat of
yeah.
like, can we sort of quantify? This really gets at the heart of what I was thinking about. Of
Hmm.
can we quantify what this difference is? Because this might be big, right? It might just be that our generative model, if you now find any solution that adheres to the constraints, you
Hmm.
have a garbage solution.
Yeah.
Because the thing that our model can represent and
Yeah.
that our model also is close in KL is very bad. And that's then also maybe why we need this trade-off or still need then some knob that we can tune, like some lambda that tells us,
Mhm.
oh, don't actually adhere to the constraint because you will get garbage if you really adhere to the constraint.
Yeah.
Just go a little bit toward it and stay close to the usual old generative model that you are.
Yeah, exactly. That's a good point. Yeah, so we do kind of need this knob because you're exactly right that if the constraint is very extreme, for instance, you have to move very far from your pre-trained generative model, you're right, you might just like produce garbage. So there, I think, yeah, the relaxed framework is really nice because it gives you this knob lambda that in practice you can tune it and see like, okay, when I make lambda too large, I remain too close to the base model. When I make lambda too small, I just get absolute garbage because I move way too far from the pre-trained model. So it really gives you this knob that you're sort of able to turn and able to see, yeah, like what does the quality of samples look like when I make lambda too large versus too small.
Yeah,
Um,
and also maybe I'll add to that real quick, which is that like it might be especially important to have the lambda if the constraints are completely not realizable in the space of generative models. Um, in which case in which case the reward framing would take you kind of infinitely far away from the base model. Um, so yeah, lambda lets you like get close to satisfying the constraints without completely blowing up the model, similar to what Henry said.
yeah, great point, Nate. Yeah, so Nate's point, yeah, like if this constraint actually isn't even realizable, there's no solution, there's no generative model that satisfies this constraint. um Sort of we'll see that this reward framework doesn't really work. But like I said, so the point here is like in order to relate this to a reward fine-tuning problem, we're going to notice this connection to the maximum entropy problem, which was introduced by Edwin Janes in 1957 in the context of statistical physics. But what it says is when we replace in the calibration problem this p theta with now a general probability distribution p, so we want to find the closest probability distribution to our base generative model that satisfies the constraint. This guy actually has a closed form solution. What it tells us is that the closest generative model to our closest, sorry, probability distribution to our pre-trained generative model that satisfies the constraints is of this form. It's just the base generative model tilted by this exponentiated. I'm suggestively calling it a reward, where our reward is just a linear combination of the components of our constraint function h of x. And the linear combination, the coefficients of this linear combination are given by this vector alpha star. So you'll see this actually looks identical to the distribution targeted by these reward fine-tuning algorithms, where in this particular case, we've shown that the reward takes this very particular form. It's just equal to h of x, like the components of h of x weighted by these coefficients alpha. And in particular, there's this very particular vector alpha star, which both satisfies the calibration constraint and is the closest distribution in KL distance to the base generative model among those satisfying the constraint. So the point here is that once once we've sort of removed the constraint that P belongs to the class of generative models, we now get a closed form solution to what the solution to this calibration problem looks like. So here's another picture. So like I said, P theta star is the closest generative model to the base generative model that satisfies this constraint, which is in black dashed line. But now this maximum entropy solution, P alpha star, is the closest distribution closest probability distribution to the base generative model that satisfies the constraint. But now notice here that this P alpha star actually lies outside of the purple blob, meaning it can't be realized by a generative model belonging to the same class as the base model. Um, so yeah, the point is like once we sort of consider this expanded problem where we now allow ourselves to consider this fully like white blob here of all probability distributions, we know exactly sort of like what the distribution we should be targeting looks like, right? It's just this P alpha star, this maximum entropy distribution.
Can we just go one slide back to do some additional digestion?
Sure.
Uh, so we have our this R alpha, and you're saying that we now like want to just do reward fine tuning with R alpha,
Yeah,
and yeah, we construct R alpha as like some weighted sum of like by weighting differently weighting the stuff that goes into our expectation computation, so to
exactly.
say. But
Yeah.
how do we find the weights then as the
That's a good
question, I
question.
guess? And probably what comes on next slide. Okay, so we now need to find these weights, and okay, sounds good.
Yeah, no, exactly, Hannes. You're too good. You're already thinking about what I'm going to present. But yeah, so the point is like in order to actually turn this into a practical algorithm, we know that we need to this will be the form of our reward function that we want to use in reward fine tuning. But what we need to do is we need to figure out like what are the coefficients going to be in this linear combination? What is the alpha star vector going to look like? So what we do is we draw independent samples from our base generative model. Notice that this is the base model, it's not the fine-tuned model. And then we can compute an estimate alpha hat n using these samples of alpha star. And I'm not going to go into the specifics of how we do this, that you can see it in the paper, but all it involves is like solving a convex program. So this is like something you could do in like CVX or your favorite um, yeah, convex optimization software, but we compute this estimate alpha hat n of alpha star. And moreover, we show in our paper that when you draw many, many samples from the base generative model, this estimator alpha hat n will approach this like true linear combination alpha star that you want to realize. So it gives us sort of this way of estimating this optimal
Mm.
linear combination alpha star transpose h of x.
Okay, so we have our h of x, right? And we now have many x's. We have x1, x2, x3. And
Yeah,
then we have the h of x1, the h of
yeah,
x2, and the h of x3. And
yeah,
now you're like, aha, I now can take my average
yeah,
over h1, h2, and h3 equally
yes,
weighted, and then I get my expectation of h. And now I
yes,
want my expectation of H to be the same as H star, but
exactly.
they're not.
But they're
So
not.
now, what are the weights that I need to assign to each of the samples that I come from my base generative model, such that it is the most similar to the H of X, the H star? And
Exactly.
then you're essentially now saying, aha, you produced this X here, X1, you
Yeah,
produced the X2, and
yep,
the H1 that you produced, it looks like the H star that I want. The H2
yeah,
doesn't. So let's
yeah,
weight up the H1, please, more and go into that direction and fine tune in that direction.
exactly. That's exactly what this algorithm looks like that I'm sort of hand waving away. Exactly, you're right, Hannes. You
Okay.
just draw a bunch of samples, then you look at the empirical average of h of x on these like samples that you just drew, and then you reweight according to like these empirical averages. That's exactly right. Um,
There's also some like intuitive alpha like values if you have like one hot encodings of classes and you're just rebalancing class proportions, for example, then like alpha star looks like the log probability ratio of your target probabilities to your current probabilities for each class. So yeah, like if you're upweighting, if you want to upweight a class, then you get a large positive value. You want to downweight a class, you get negative values in that alpha
Do
vector.
you have an algorithm also later on the slides? If so, then
so
I'll
for
make my
you're
comment
interested in like
there.
what this particular problem looks like. Yeah, I didn't include this in the slides just
Okay,
because. it is a bit of a rabbit hole, but I would encourage you to like look at the paper. It's all there. And like you
No, no,
said,
no. Then, so I was just asking because then I would have made my comment later on that slide. But then now, so what we do is I have my base generative model. I
hmm
sample from it. I
hmm
look at the samples and
Yep.
then I check, is their age, is their age nice? Is their age
Yeah,
close to my age star? And
exactly.
if yes, then I include them in a upweighted fashion in my fine tuning to be more similar to that H star.
hmm
And if not, then we include them a little less in the training objective,
Exactly.
give them a lower weight in the training objective. And that
Exactly.
is opposed to CGM relax, where we just look at the difference
Exactly.
between the two.
Yes, that's exactly right. Yeah, so in this, you're right, Hannah. So like if I need to like increase the proportion of cats in my fine-tuned model, then my alpha hat will be like super large for the class of cats, meaning that I'll like really want to jack up the proportion of cats in my fine-tuned model. Versus if I want to downweight them, it'll be a very like negative value where I means, yeah, I don't want to sample as many cats in my fine-tuned model. So you'll see, yeah, like Nate said, this alpha hat is like very intuitive. So the idea is, yeah, we don't know what alpha star is in this maximum entropy distribution, but we show that in the limit of drawing many samples from the base generative model, we can estimate it to very high accuracy. And then what we do is we just turn this exactly into a reward fine-tuning problem, where now our reward is just equal to this R alpha hat n of x. So it's just this, like I said, this linear combination of the components of h of x, where the coefficients of this linear combination are now given by this approximate alpha star vector that we found, this alpha hat n. So yeah, so this should look very familiar to folks. It's just exactly the reward fine-tuning objective for this very, very specific incarnation of the reward. Like I said, which required us to first estimate this optimal alpha star vector by drawing a bunch of samples from our pre-trained generative model. And then the idea, like Nate said, for the CGM relax is that we can compute unbiased gradient estimates to this guy by estimating the KL, by estimating the KL as well as this expected reward term in this reward fine-tuning objective. So it should look very clear from this sort of like purple box here how we would actually optimize this objective. It's hopefully I'll push the details away just because yeah I want to make sure we get back to the examples that we presented at the beginning of the presentation. Great. So now that we've discussed sort of our two algorithms, how do they actually apply to these two case studies that we presented, this diversity and protein structure diffusion models and these gender, occupation, bias, and language models. So in this case, we'll take our pre-trained model to be the Genie 2 model. Sorry, Hans, did you have a question?
Can you just remind me again, our R alpha star slash R alpha hat,
Yep.
is that now just the H times alpha star?
Yes.
And
Yeah. It's just a weighted
yeah,
combination of the components of H, where the weighting is given by this like alpha hat vector
yeah.
that we computed.
Um, and then we say, but this H, like what if this H function is, mm, no, no, no. We're taking the average. It's just like taking the expectation, but now
Yeah.
it's taking. Okay, and now we already can think about the question of if we now have biased samples coming from our model,
hmm
then the reweighting from our biased sample then probably would just change our alpha values a little bit,
Yeah.
right?
Yeah.
um, like if we produce our like the samples that we then put into our H and then
hmm
we compute this alpha vector for it, we now don't get these samples just by sampling our base generative model, but we can get them by sampling already from the tilted distribution
Exactly.
with inference time steering.
Yes.
Then we also have these individual weights and they are
Yes.
now just they need to undo a little bit of the
Yeah.
alpha weights.
That's a really good point. So
Okay.
yeah, the way that we compute this alpha hat now is just by sampling from the pre-trained generative model. But Hannes, you're exactly right. You could instead like sample from like a steered version of the base generative model, and then just account for that fact when you're actually computing the weights by doing this like reweighting step. You're like, I
There
think
you
that's
have
a
another
yeah.
paper.
Yeah, I think that's what you were suggesting, right? And the
Yeah,
reason to do that might be like if your base model is very far from the fine-tuned model, these like your alpha hat n estimate could have like very high variance. Whereas like if you use this like sort of steering-based approach, you could potentially get lower variance estimates to alpha hat. I think that's what you were suggesting, Hannes, which is
yeah.
a very good idea, which we did not explore in this paper, but I agree this is something that we'll look into. So yeah, coming back to this Genie example, what we'll do is we'll make our base generative model just this Genie model with this reduced noise scale. And the reason for using this reduced noise scale is, like Nate said, a very high proportion of the structures that we sample from this model are biophysically plausible as measured by this designability metric. And then we'll define our calibration constraint h of x by looking at the empirical cumulative density function of the secondary structure of the Cath domains. So what this means is we'll just like chop up the distribution of the Cath domains and then like define our um, h of x using these sort of like rectangles in this bivariate CDF plot. So I won't go into too many details just for the sake of time, but the idea is, yeah, our constraint function is defined in terms of this empirical CDF of the Cath domains. And for CGM reward, we use up to, sorry, for CGM relax, we use up to 99 total constraints. So 99 total quantiles that we'll want to fine tune to. So what does this actually look like in practice? Well, like I said, we start with these very alpha helical structures. And what we see is that as we continue, as we sort of iteratively refine our pre-trained model using the CGM framework, we gradually push our model to produce these structures with a higher proportion of beta strands. So to put some numbers to things, on the x-axis here, we have the proportion of design failures, so the proportion of structures that aren't designable. And on the y-axis here, we have the miscalibration, which is the symmetric KL distance to the Cath domains. And this is like the symmetric KL distance of the secondary structure distribution. So we see that by applying the CGM framework, we get a roughly 5 times improvement in terms of the KL distance to the Cath domains in terms of secondary structure similarity. So in simple terms, our proteins that we get after doing this fine tuning look 5 times more like natural proteins than do these proteins that coming out of this like reduced noise Genie 2 model. And moreover, you'll recall that the issue with the original Genie 2 model with noise schedule 1 was that only around 25% of samples are biophysically plausible. And we see that in this particular case, once we do the CGM reweighting, once we do the CGM fine-tuning, still we have around 86% of structures being designable. So we're sort of able to solve this trade-off between diversity and biophysical plausibility, right? We're able to both sample proteins that look a lot like the proteins coming from the Cath data set, and we're able to produce structures that have a very high chance of being biophysically plausible. So like I said, there's this previous trade-off that Nate introduced where we could either have high designability or high diversity. And here we've shown that by sort of taking our pre-trained model and calibrating it to the Cath domains, we're able to achieve the best of both worlds in this particular setting. And then, like I said, the results for CGM reward are more modest. It stays closer to the base generative model, but it still improves the diversity by more than 2 times. Great. And now Nate's going to discuss this gender occupation bias and language models setting.
Yeah, so for our base model, we'll use Gemma 2 9 billion instruction tuned. This is a fairly recent open language model that was pre-trained on 4,000 TPUs and then fine-tuned for instruction following, which let us prompt it to ask for short stories. And while it works well in instruction following, it's very prone to stereotyping by profession, as we saw earlier in this bar chart. And we also saw that we can't just prompt the problem away. We did try asking for genders with equal proportions in the generated stories, but this is not the kind of instruction that instruction tuning and tuned models are typically trained for. Um, so yeah, we'll try applying CGM, and this is a little bit different from the other problem in that we want a sort of conditional calibration. We want calibration gender balance per profession. So, uh, In order to do that, we'll just apply CGM per profession in each training batch. So you can imagine a separate CGM loss for each of the 8 professions we're calibrating on. And so even though that requires fairly large batch sizes to get low enough variance gradient estimates for each profession separately, we're still able to fine-tune Gemma in only 6 hours on a single H100 using LoRa compared to, yeah, the 4,000 TPUs it was initially pre-trained on. So yeah, here we have gender imbalance on the y-axis and a measure of distance from the base model on the x-axis that is we picked because it's sort of fair to the baseline model, the baseline approach. And so yeah, the star shows the like sort of idealized max ent solution. And then above that we have CGM reward, and then above that we have the baseline method. And so yeah, its CGM reward outperforms the baseline method a little bit on miscalibration and while preserving the same distance from the base model. And then, like we said, CGM relax lets us explore the trade-off between the two, gender imbalance and distance from the base model. And we can reduce up to 3 times more miscalibration compared to the baseline model using CGM relax. And then if we zoom in on one of these best calibrated models and then look at each profession, we see that, yeah, as expected compared to the base model, we have much less gender imbalance per profession. And then we also explored what would happen if we looked at 6 professions that weren't explicitly calibrated for. And so interestingly, 4 of those 6 professions get better calibration, even though they weren't targeted by the objective. So we see some sort of interesting generalization of the calibration, although a few of the professions were made less calibrated. So this could be another interesting direction to explore for future work is like sort of generalization to different conditions. Maybe if we trained on enough professions, then we would get calibration on all of them and not have those 2 that got worse.
Yeah, great. So in the interest of time, I'm just going to very briefly wrap up. So we've shown that CGM provides a very general strategy to incorporate distributional constraints into generative models. It's very lightweight. As Nate discussed, we can fine-tune a 9 billion parameter language model on a single H100 GPU in 6 hours. It's effective at reducing a majority of miscalibration across all the applications that we've considered, which also consider a very wide variety of generative models, from normalizing flows to diffusion models to autoregressive language models. It's scalable to very high dimensional generative models like diffusion models, and it's also scalable to high dimensional constraints. We showed that it applies to up to a 99 dimensional constraint in this protein diffusion model case. In our paper, we showed examples where we applied to even like 1,000 dimensional constraints, and it still reduces the miscalibration quite effectively. So yeah, thank you to Brian, who advised us on this project and was provided really invaluable feedback. And thank you also, Hannes, for the opportunity to present at your group meeting. It was great to hear your thoughts on the paper and yeah, share our work with the audience. We're super appreciative.
Amazing. Thank you. This, like, I really like the right, it's kind of intuitive. You sample your model and then you have the ones that are nice, the ones that aren't so nice. Now train more with the ones that are nice. And
Exactly.
so you upweight like this instead of taking a loss where you just yeah, look at how far you're away from being nice, and then you need to backpropagate, or then you also need to backpropagate through that somehow. And yeah. And but then there's this nice piece behind it of, I guess, this information theory perspective of this maximum entropy problem, and then knowing that, yeah, this actually makes sense and this is the distribution that you get. It's very cool. And then you can also draw these diagrams, and then I guess there's also some information geometry there that probably one can draw out, where
Yeah.
like you have your KL and then your maximum entropy solution is somewhere there or something like that. I don't remember all that stuff, but yeah, it's very cool.
Thank you.
Yeah, then let's go with some more questions, I would say.
Sure.
in the chat, we have in regard to reinforced style score function estimator. I'm having a hard time understanding how this approach maintains stability for complex systems like so. First of all, what do you actually use in your experiments now? Relax or the other one?
Oh yeah, so we show both of the first we
Oh,
show both of them. Yeah, so in general, yeah, like we show both relax and reward for this like protein cases in this red triangle, and then relaxes in this blue circle. I mean, like I said, we're able to try to sort of reward in general will stay closer to the pre-trained models, so it's sort of more conservative. We observe that on average it wants to move less far from the pre-trained model, whereas by making this like lambda super small in this relaxed objective, we're able to satisfy the constraint better, but move further from the base model, which I guess is like kind of intuitive. It's sort of like a lever that you
yeah.
can tune. But yeah, we have all results are shown for both of these strategies.
Okay, so I guess the reference and the question to reinforce style makes me think it's about the CGM reward. But
Mhm.
then the rest of the question is, since score function estimators are often noisy, could
Yeah.
you explain how you achieved convergence with a batch size of only 64? Did you find the leave one out baseline was enough to handle that variance?
Yeah, that's a great question. First of all, thank you for the very insightful question. So yeah, the point is that we use these like score function or reinforced based gradient estimates to actually take gradients of these objectives that we've written down. And it's sort of well known within the literature that these score function gradient estimates suffer from very high variance. Um, so what we do is we use this leave one out baseline, which is in RL, it's sort of this term that you add to your gradient that has expectation 0, but is known to reduce the variance of your gradient estimator. And we do see that this is like effective at reducing the variance, even in these very like small batch size regimes. But yeah, we are still exploring further ways which we might be able to get away with an even smaller batch size by reducing the variance of our gradient estimates even more. One possibility there is, for instance, using an off-policy proposal distribution, which is similar to what Hannes suggested, rather than sampling from your current generative model, sampling from another generative model that might give you like lower variance gradient estimates. So this is what we've done, but again, like we're not claiming that it's like optimal in terms of producing the lowest variance gradient estimates.
Yeah, I would add it's like kind of a nice surprise. It was almost a nice surprise to us that the score function gradients were good enough to optimize on. Like I think we were kind of yeah, pleasantly surprised that we could get away with these smallish batch sizes and not very many epochs to get convergence.
Yeah, the other or the I've always forget the name, the non-reward objective.
Mhm.
No, no, the non-relax objective. So the reward objective. Um, I like it more. It's like
Mhm.
it seems so flexible. Now you can play around with it in so many other ways,
Mhm.
and so controlled. Anyway, then I would, can we maybe, as last question,
Sure.
talk a little bit about your constraint that you're using to optimize for high helicity or so, like where you have these CDF functions. How does
Sure.
that work in a bit more detail?
Sure. That's a good question. So how do we actually define the h of x function using the CDF of the cath domains? That's a good question. So what we do is we chop up the CDF of the cath domains. So like I said, here we have the x-axis is the proportion of residues in an alpha helix. The y-axis is proportion of residues in a beta strand. So what we say is that like in the cath domains, we see that around 50% of the structures in this domain have percent alpha helix at most 40%. So around 50% of the structures have percentage alpha helix at most 40%. So that becomes one of the constraints. And then we see that around at most 90% of structures have percent alpha helix, at most 60%. So this sort of also becomes another constraint that we add. So what we're doing is essentially we're looking at the quantiles, what we call like the quantiles of this bivariate cumulative density function of these like cat secondary structure. of the cat secondary structure.
Okay.
So we,
So it basically you compute a histogram
yeah,
of your natural distribution.
yep,
And then before you do any training, you go
yep,
ahead and you sample your base generative model a whole
yep,
bunch. Now you
yeah,
have these two distributions, and
yep,
then you compute what are the weights that I need to reweight something from my model distribution to have instead been coming
exactly,
from my target
exactly.
distribution. And then these weights are what you then, like at training time, you'd go ahead and you sample a new, and then you see, aha, it has this much helicity, and
Yeah,
therefore the right weight is this one to reweight it
exactly.
to come from the distribution that I want.
Exactly. So yeah, that's the point. Like if there's a bin, like for instance, with like a lot of structures with around 40% helix and around 20% strand, like under the base model, like this bin of the histogram, like you said, Hannes, will have very few samples in it. And we know from this cap domains, this bin should have like many, many samples in it. So this should tell us like, aha, what we should be doing is like reweighting the samples very highly that we sample from this bin under the base generative model. So hopefully it's like kind of
Yeah.
intuitive. It's exactly what you said.
I really feel like now it should be helpful to have sort of a like right because your importance weights if you have your one distribution having support here and the other
Mhm.
distribution having support here, then you will be very inefficient with your fine
Yeah.
tuning because your weights will all be very low.
Yeah,
And now if we can instead have some like I don't know start with fine tuning toward this distribution
yeah,
because we have like we use some like no not doing this fine tuning step but doing this fine tuning step
hmm,
because now we have some target distribution that maybe we do some steering with the samples
yep,
that we get and we already move our distribution a little in that direction. Then yeah, probably you can sort of have a gradual shifting
yes,
toward
yeah,
um, the distribution that you want.
exactly. Yeah, there's actually been quite a bit of recent research that's come about this within like the reward fine-tuning framework, whereas like as opposed to jumping straight from the pre-trained model to this target model, what you'll do is you'll define like a sequence of intermediate targets. So you're like
Yeah.
gradual more gradually moving towards this solution that you want to find rather than jumping right to it, like you said, Hannes. These like
So is that
these trust
do they?
region based approaches, I think they're called like KL or trust region
Ah,
based approaches, where you'll define like a sequence of like intermediate target distributions, which aren't equal to the distribution you ultimately want to sample from, but are like closer to your base model. And then you'll iteratively move your generative model towards the ultimate target distribution, if that makes
okay.
sense.
And are these most of the time like constructed by some sort of annealing or yeah? How do you
Exactly. Yeah,
usually
exactly.
make
You just
the?
you anneal the reward is how you construct it. You
Ah,
you put a
okay.
parameter on the reward and then you increase that parameter to make
Mm,
it. Yeah.
okay. Okay, well, cool.
Yeah.
Thanks for the nice talk and discussion and telling me a little bit about the literature that's here in
Yeah.
that space. And yeah, if you have any last words, then now's the time. Otherwise, we'll call it a day.
Yeah. Thanks again, Hannes. This was a really great discussion. Thanks for all of your super insightful questions. And it's funny that, yeah, many of the things you brought up, we've already been thinking about since you put out this paper. So really great to get that feedback.